sort of strange in-situ electrochemistry of nitinol mechanically cycled in fluids. So what we did is that probably most of you came across the corrosion experiments, electrochemical experiments, where you put the material into a fluid at the voltage and measure the processes at the interface between the metal and fluid which occur. And this is important for corrosion because the metal, when it's exposed to corrosion, it degrades and you have problems. And this occurs, corrosion takes place the years, but you want to study it in the laboratory, so you accelerate it with electrochemical system. So you have some electrochemical cell. You have inside the material, you have the electrodes, put the electric current, you accelerate the corrosion, and you determine it statically. And the nitinol, as I said before, is protected by very thin oxide. And so the people who try to optimize this oxide, they use these electrochemical experiments on nitinol with different oxide to find which is best for implants for human body. And this is all big science about optimizing to surface oxides on nitinol for implants. But we made some SEM observation. Maybe it is here. Okay. Well, okay, I have to jump here. This is I will go back to the beginning, but so when we look on the nitinol, which had surface oxide basically uncontrolled, something like 150 nanometers thick. After one superelastic cycles, when we look at it, we found with high resolution SEM that there are cracks in this oxide. And everybody who is doing the corrosion knows that if you have the surface with some kind of crack in the oxide, this is a problem. But on the other hand, this okay. So the first experiment, what we did was that we made the sample, stretch it, broke the oxide, and then put it into the biofluid for 1 day, 1 month, 3 months, and after that check what happens. So when we compared the properties of the wire with the cracked oxide after 1 month, 3 months, no effect. It was the same. So there was no damage. The cracks made no damage. But still, we had the Czech company who makes the esophageal stents, and they came with the pictures of stent which was completely corroded and told us, tell me why this corrosion happens, because the stent was supposed to survive something like half a year, and after 1 month the patient died because the stent was completely corroded. And so they were for these people, such kind of failure is crucial because it can kill the company. And so we had the problem to find out. We thought these cracks might be blamed, but the result of the experiment was zero. I mean, cracks made no problem. But when you have the stent in this esophageal stent, so when you are eating and the stent is working actively, and these cracks are opening, closing, opening, closing. And in corrosion experiments, if you what does it mean? It means that every time the wire is stretched, and because the nitinol wire deforms 5%, so you have surface strain 5%, and this ceramic oxide cannot survive 5%. So what happens is that these cracks which appear in the first cycle, upon further cycling they are opening, closing. We could see it. If we put the sample in SEM inside and look at it, we have seen how the cracks are opening, closing. It's even such that you can see the cracks in the oxide only if you look on the nitinol under stress, because when you unload, it will close, the cracks will close, and you will not see them. You know, even the SEM doesn't have such a good resolution, it will be very, very tiny. But when you stretch it, the cracks will open, and suddenly you see there is 1 micrometer black track of the crack. So we thought that the source of the problem is not the crack itself, because when two cracks are exposed to biofluid, the healing process immediately starts. The cracks are filled by another oxide, and it's protected, and the problem is solved. So the material solves the problem when it's static. But when it is dynamic, maybe this was the idea. We didn't know. So I will go back to the start of the talk. So then we thought this may be general, because you can have problem with two cracks, and even in common environment, because if you have a micrometer crack which open and closes, there could be fluid in it, and these corrosion problems can start. So then we were excited. It could be the problem of fatigue. So when I prepare this, I just show it broadly. I search in the literature whether there is some difference between nitinol and steel, for example. But this is from the article, very nice review article, Fatigue and Fracture of Wires and Cables for Medical Application, where one can compare the overview on the fatigue data from stainless steel and nitinol, and you find out that for the similar amplitude, even though for this is 6% for nitinol, is almost acceptable, but 6% is definitely not acceptable for steel. But still, the spread of the data and these curves are kind of similar. So the review of the literature said it probably doesn't play much role. But still we have this problem with fatigue in many applications. Elastocaloric cooling. You have nitinol in fluid, and there is a question whether this plays a role or not. You have any kind of actuator. If the environment, there is some moisture, you would have the same thing. You have this dumping of civil engineering applications with these martensitic wires. You can have cracks in the surface oxide as well. So this is kind of overview what could be the potential sources which have to be taken into account when looking at the functional fatigue of nitinol. So first of all, it is this strain compatibility, the austenite-martensite interface. This is still relevant. It should be problems with this localized deformation, because when we do the test in wire intention, we will have it. And of course, when the deformation is localized in such kind of band, there is a very, this localization is really a problem for fatigue. Imagine that you have this, but now you stop. Go on. And now you stop here in the middle, and you start to cycle. Yeah. So what will happen? You will cycle, and the band will move like this. So you apply the amplitude like 1%, but you will have 10% here. And of course, this localization, this is a killer for any Fortunately, if you do that, the localization will spread and the sample will somehow deal with that. But it is definitely a problem which have to be considered in functional fatigue. No, and we added this our mechanism with cracks here and hope that maybe the cracks are all. Yeah, sorry, no, this is different. This is the most famous topic in the medical field, and this is the fatigue failure due to damage at inclusions. We talked yesterday, day before yesterday, on about the presence of carbides and oxides in nitinol, which is casted in big ingots. And so you have always the carbon and oxide coming into the material. Then when it is annealed at high temperature, the carbon and oxide stick together and create the particles. The particles are quite 10 minutes. Yeah, the particles are quite big. And then when people look at the surface where the cracks are initiated, they are always initiated at the holes at the surface where from these carbides and oxides are gone. So the companies who make these nitinol wires, they are of course try to solve this question, and they solve it by basically they are not able to get rid of the oxide and carbon and oxide, and so what they can do, they do lots of arc remelting and deformation in such a way, extrusion in such a way that these oxides are destroyed into very, very small oxides, and then they don't make this problem. This problem occurs when the oxide is like 20 micron big. When it is 1 micron big, it makes no harm, and the number of cycles, superelastic cycles, can increase up to 10,000, 100,000 from the 5,000. So this was solved, and it's called something like ultra clean, damage tolerant nitinol, and now most of the producers start to use those ingots only, because it's a new quality of the ingot. Yeah. So I spoke about the cracks on the surface oxide. So let's look again on how the surface of nitinol wire, which is used in application, look like. So because of titanium, in nickel titanium, if the nitinol is exposed to atmosphere, it will start immediately to oxidize and form an oxide. If you expose it to the oxide at a higher temperature, there will be thicker oxide. If you do it at room temperature only, it will grow for days or years, and it will be uncontrolled. So what is done normally in any company which makes the semi-products for medical devices is that they electropolish the surface and then perform some control oxidation in controlled atmosphere for short time. Of course, when you buy kilometers of wire on a spool, it is done by heat. When the wire is spooled from one spool to another one, goes through a tube which is filled with limited amount of oxide, and it goes through about 2 minutes, and during this time the oxide grows to say 100 nanometer. So the speed of respooling and the temperature and everything is designed not only to control the microstructure of the wire, but also to control the quality and thickness of the oxide. So as a result, you will have an titanium oxide, number one, which could be something between 10 nanometer and 500 nanometer thick. And because if you have the oxidation, so this titanium from the metal reacts with the oxide, so it's taken from the matrix, and the matrix underneath will be nickel rich. And if it is nickel rich, the MS temperature will go down, but it's only very thin layer. But you always have a nickel rich layer underneath the oxide, and this could be a problem because in medical devices many people are nickel allergic, and if you have the layer which is enriched with nickel on the surface of the metal, it's a problem. And so this is the nickel rich subsurface layer, and then you have matrix with grains. And one additional problem, sometimes you have these carbides or on the surface, and then there could be a source of hole, cavity, and this cavity, when you do the cyclic test, becomes frequently the center of main damage, which finally grow to the major crack. So I already spoke about that. But now we can get rid of the carbides, so the problem is with the oxide layer itself. This is some experiments with XPS depth profiling, showing what is the thickness of this nickel enriched. So nickel is the blue, is the nickel. So you see here something like 20 nanometer thick layer which is enriched with nickel. This is the red is titanium oxide is on the surface, so it is underneath the surface layer. I already said that when we bend the wire, the oxide layer will crack. So we perform some experiments on the bent wire with cracked oxide, and it has somehow different response in potential current density electrochemical tests. But I already said that these measurements, simply the response from them was negative, and we had this problem with the oxide which are cracking. So here you can see the same image where under stress there is the moving macroscopic band. Here the oxide is undamaged. Here there are cracks, and there is some periodicity which would be almost like 500 nanometer here. And if you take different oxide, it would be 100 nanometer. It could be 20 nanometer. It could be 1 micrometer. It depends on the thickness of the oxide. The thicker the oxide is, the less cracks you have and more separated, and they are wider. So if the oxide becomes very thin, we don't see these cracks because they are too thin. Even under, if the nitinol is fully stretched 5%, there are millions and millions of very fine cracks which cannot be resolved in the SEM. So you may ask, how do I know about them? I will explain soon. So what we also can do, we can subtract from the surface lamella for transmission electron microscope observation, and then look in SEM and TEM on the crack from the side. This is the demonstration which I said how the crack looks like under stress and without stress. Stress-free, 6% strain. You clearly see the cracks. Here you see almost nothing. But well, you still see them, but because they are too big. But if they are less big, you will not see them even under deformation in SEM. No, so So then when we learned that this healing will solve the problem if the cracks are not periodically opening, so we came to the conclusion we should make some experiment where during the experiment the cracks will open and close, and we will try to observe whether there is any reaction with this electrochemical experiment. Because if you measure the electrochemical potential and you have the electrode, this is sensitive to the layer which is on the surface, basically only to the oxide. It doesn't see the metal. But immediately when the bare metal is open for the fluid, the potential is changing. So we thought we might be able to detect this cracking by detecting the electrochemical potential. But we needed to make the experiment for that. So the experiment for that looks like this, where there is a tester, there is an electrochemical cell, the sample is one electrode, another electrode is just submerged into this cell, and we measure the potential between the fluid and the electrode, which schematically it is shown here. And this is just like schematical picture which shows the metal matrix. There is this blue is titanium oxide, and here there is a crack which opens, and by the blue color this is also titanium oxide, but a very different one from that which is created by oxidation. This one is created by the electrochemical reaction. Because even if we measure the OCP, if you have the metal in the fluid, there is immediately the electrochemical potential, and this speeds up the corrosion process. So the corrosion process in fluid is much faster than in the, so it's the same philosophy like that like corrosion test which is performed on metal, but here it is performed dynamically. And the process of this reaction is this yellow, it's like a gel, and it covers the surface of the crack. No, so we have this experiment, and now this is what we measure. So okay, we are interested in cyclic deformation, but before going to cyclic deformation, I have to understand what happens during single load. So in a single load, you just strain here. So the profile, this is time, this is strain. So in some moment when the bend goes through the place, it deforms like this. So the stress is increasing and goes like this to the end. So we measure the electrochemical potential, which is basically the voltage on the interface between the liquid and metal, and when we are loading, and immediately when the band is opening, the OCP goes down, but while it is propagating, it goes up. So it can only be explained by the fact that these reactions are extremely quick, and this agrees with the literature. These reactions are really extremely quick. So after very short time, you will have such kind of healing, and after 1 second, you will have already OCP, which is increasing back halfway from the value where it was before. If you cycle elastically only, there is no cracks. This OCP will stay approximately constant. So this can be explained basically as a two different chemical reactions, which are classical one for anodic passivation and cathodic reduction, which proceeds simultaneously in the moment when the bar metal is open, is put into the contact with the liquid. So we know this, but the question is how it looks like on average, because you don't have just one cycle, but typically these implants, when they are in the body, they are supposed to be cycled supraelastically. I mean, this is not the case for the coronary stent, but it is the case for this esophageal stent, and our problem was given by this medical company to tell them what is the reason why these esophageal stents degrade so quickly. So we did the measurement of OCP during the supraelastic cycle, and the response is here. So in the beginning you have this decrease, and then the healing during the rest of the cycle, and again decrease, and again. So this is how it looks like in time. So basically our concern was confirmed. Yeah? So when for the first time when the cracks appear, the OCP goes down, because this is not just one crack, these are millions of cracks everywhere here along the surface. But as you are cycling, the passivation proceeds, you can heal it, but the value is still half. This change of almost 150 millivolts, this is very big change in open circuit potential. So we have a good reason to believe that somehow the corrosion process which proceeds is now localized into these cracks which are opening and closing. If they remain open, there will be no problem. The problem only is if they open and close. So again, there is a problem. What does it mean for the metal if you have a surface covered by such kind of cracks which periodically open and close? We didn't really know. So we made many different type of experiments to understand that. We made springs because the stent is like a braided stent where the wire is shape set into the coil. So we wanted to know what is the effect of this. But the result was more or less the same, which I explained before. Here we were interested whether there is any effect of rate, how quickly we cycle. We can cycle slowly. So if you cycle slowly, the cracks will open, then there will be lots of time for passivation and close. If you cycle quickly, you will not have this time for passivation. You know? So really, there is the effect of strain rate. The faster it is, the lower OCP you get. And then this is the main problem is that if you have a stent, the deformation on the surface is not homogeneous. You have some parts which deform supraelastically 5%, and some parts which remain elastic. So we wanted to know, what about if we cycle only elastically the austenite, or if we cycle in the middle, or if we cycle, so we did such kind of measurements for strain amplitude and pre-strain. Pre-strain is more interesting. So you see here, if we cycled between 0 and 400 megapascal, but in elastic range only, the OCP slowly degraded up to something like 10,000 cycles. So because in this experiment there were no cracks, it never cracked. But as you are cycle with in this range between 0 and 400, somehow probably the surface degraded, and because of that you have this kind of decrease of OCP. If we did the same, but we cycle in martensite, so there is a constant stress like 500 megapascal, and we cycle plus minus 50 megapascal something. So the response of the sample is elastic. So in that case, the long life was maximum. This is in logarithmic scale, so something like 30,000. And in the middle, there are only 1,000. So 30 times higher long life in martensite state, where the stress is larger and amplitude is also large. So it's very counterintuitive. You have the wire, you have large pre-strain, large amplitude, and long life, and then you have here and you have short life. So why is that? Well, it is shown here. So in the elastic range, the surface oxide is cracking only at the end of cycling. In the beginning, so there is very little damage. So the OCP remains high. In case of martensite, we have fully stretched the wire, and but then upon unloading, we never go back with the strain, because we keep this pre-strain and cycle. So the cracks remain open and thus only do like this. So the passivation proceeds and it never breaks. So if you are cycling with fully pre-strained wire, you don't have this fracture and opening and closing, because the cracks are open all the time, as it is shown here. And the passivation proceeds, and finally this sample has longest life, 30,000 cycles. And in this range, where you cycle supraelastically, so the cracks always open between 0 and 5% strain. So even if there is some this gel created upon next opening, it fractures, and so it's distorted, and again and again and again. So you have this condition under which the cracks are opening, but we still don't know why, in which way it affects the long fatigue life. Yeah, we only know that we have some sort of mechanism which could be related to this, which probably works. But if one thing, okay. So we were consulting these things with chemists and with people involved, because at that time, it was like 10 years ago, we did this work. I haven't found anyone in the literature who did a similar dynamic corrosion experiment, so it was difficult for us to find the answer. But we came by discussion and looking at the theory to the conclusion that in fact this kind of the problem is this repeated passivation process at the surface, because when this happens, a lot of hydrogen is created and hydrogen is pumped into the material. So for this you need, this is the passivation, yeah, and in here this passivation occurs in the same place again and again and again for the thousands of cycles. So you have actually something like electrochemical pump which generates the hydrogen at the surface, and the hydrogen is pumped into the matrix, and after some time you find the cracks which are underneath these oxide cracks. So this is shown here by the transmission electron microscope. We found that you have the many oxide cracks, and under some of them you have the cracks. This is already the cracks in the matrix. And there is perfect correlation between these oxide cracks and matrix cracks. So it is clear this was taken like the evidence for this hydrogen pumping mechanism. So at the time we bought our first SEM microscope equipped with FIP column, and so with this you can if you have a surface and crack, so you can do the such kind of analysis that by fibbing the layer of the surface is milled, and picture is taken and milled and taken, and you go down and you can reconstruct in 3D the micro crack. So this is the result of such kind of reconstruction of 3D reconstruction of a defect in the metal by 3D SEM-FIP method. It's very nice, but the problem, it took like a 1 week measurement, and finally you don't get much information out of that except of the fact that it is beautiful. And these things around here, this is the carbide and oxide particles which are around, and there are really many. Yeah? One of the result of this SEM-FIP observation is that the density of the oxide is very high. So when this medical company, when they have seen what kind of oxide density they have in the wire, they were really terrified. So maybe I will not go to the detail. There is this article. In the article there is a detailed description of this, we call it like hydrogen pump. So there are important steps which I try to explain. The most important is fracture of the oxide, then creating of this hydrogen by the opening, closing crack, transport into the bulk, and the hydrogen in the bulk supports the growth of the oxide cracks into the matrix. Yeah.
So when the oxide was grown on the NiTi, it was in stress-free condition, right?
Yeah.
So did anybody ever explore to put it in tension and then outgrow the oxide? So when release it will be in compression mode, and crack opening will be lesser.
Yeah. I understand you, but as far as I am not aware of such experiment. Okay. I should end the story. Just let me. Maybe I include it in the presentation. Yeah. It is here. This is the question too. So we also discussed these results with the people in United States at the companies who make this surface finishing, and with them the discussion is somehow difficult because they don't want to disclose what they have and they want to sell it to the customers. But finally, with one of these companies, they gave us their number 1 wire, where they said this is the optimized oxide. So maybe they use something like you said, but not. Yeah, I mean maybe, but I'm almost sure they didn't do it because for them this would be very difficult to do such kind of processing. What they do is they make the oxide as thin as possible in such a way that if they put it without any stress into the material, it shows good corrosion properties, and when they stretch it, they don't test so much, they don't care about fatigue, they care more about nickel leakage. And this process, when the hydrogen digs into the material, at the same time causes nickel atoms to go out, and they can detect nickel leakage. So they have more system to determine the nickel leakage. And they optimize the wire with respect to static corrosion and dynamic nickel leakage, which would be also optimized for our mechanism and cracking. And so then they gave us two wires. One was electropolished and one was covered by this optimum number 1 oxide they sell. So then I call it HTO. This is the result of long time research how to optimize heat treat the surface oxide and how to do the electropolished. No? And so we spent lots of time with testing and analyzing this wire, and basically the conclusion was about the same, that if we test in the elastic range, we get very long life. If we test in the martensite range, we get long life. The problems are in the middle. And this is the case for both wires. But the HTO wire showed much poorer result than the electropolished wire. So the wire which had no oxide, I say no, but there was some oxide. Our measurements show some kind of damage but it cannot be seen in SEM. It can only be seen by this electrochemical. The beauty of this electrochemical measurement is that you cycle the wire, and what you see are nano-sized cracks on the surface. The measurement is only sensitive to the few nanometers on the surface. So for me this is exciting because you have access to something which is not available for my electron microscopy. Now, and this is you can go, you can look the article. You have here the results in the PPT slide, and this is the example of oxide particle, which typically cracks during the superelastic loading. You will see such kind of cracks in the oxide, and this then causes the changes. But finally the conclusion is that the mechanism works here, and this special HTO wire is not good solution for solving the fatigue problems, but overall you also have to assure the good corrosion resistance in static case, and then the HTO is much better than electropolish. So if you average, you find out that the HTO is better than electropolished. But if this is the answer for your question. So because I have time only, like how much?
40 minutes.
Yeah, 40 minutes. So I would like to go to the third. So this is the takeaway, which